sometimes, and I fall into this trap, I get some data, I build a model, I move on. And I think, great, that is a great R squared, actual versus predicted looks good. I'm crushing it. But then if you kind of pull the veil back, and it's kind of like taking your car to the mechanic, everything sounds like it's fine. And then they call you and say, well, actually, this, and this all need to be addressed. And so you kind of have to literally get under the hood of the model to take a look and kind of understand what might actually be amiss versus what is working as expected. So I'm going to teach you today, or show you some ways to kind of address or maybe diagnose your models and try and understand whether or not you have an issue of collinearity, sometimes referred to as multicollinearity. And then we're going to kind of build progressively more complex models to help address the issue of collinearity. We're going to bring in another tool that is called Principal Components Analysis, or PCA. And then we're going to kind of try and tie those two together, advanced modeling with principal components, to build a model that is kind of free of the issues of collinearity. But I think a great place to start is, what on earth is collinearity? So this is the journal that you'll have access to, so I'm just going to make this a little bit bigger. At a very high level, collinearity, multicollinearity, really at the heart of this is you have one or more factors that are highly linearly correlated. So I've made this example. Here we have a variable x1 and a variable x2. I'm using these two variables to predict y. Now, I'm going to show you here in a minute, if I build a model with both of these variables, the model is going to have a very difficult time disentangling what is actually driving this. Is it all x1? Is it all x2? Or is it 50-50? So let's take a look at that. So we build this model out. And so here's just that exact same graph. I'll just close that out. But here's that model. So this is just simple standard least squares. And you can see it is opted to say that x1 is driving this process. If we use, kind of a long-standing, quote unquote rule, this is a small r rule of removing any terms that are lower than 0.05 in our predictive models, then you can see it's just going to be all the results of x1. However, if we plot these individually against y, we can see they both have a fantastic fit, an r squared of 9.6 and 9.7. x2 is just slightly lower than x1, and I would suspect that the model identified this and is therefore opted to show that x1 is far more important than x2. But as you can see, if I remove x1, x2 becomes very important, right? It's the only one there, but it also becomes very predictive. So this is the issue we're trying to address. We want to work through this, working through an example from the aerospace industry. We're going to look at a data set that's related to a laser cutting process. So there's a number of places within airplane design, specifically jet engine design, where this might be important. We have these critical components that are, we call them combustion liners, and they have cooling vents or holes cut into these with a laser. And this is a very difficult process. The materials aren't inexpensive. And if you make mistakes, then the entire piece is scrapped. If you use a laser that is too powerful or too strong, you might damage and weaken the material around that perforation. So in order to optimize this process, we want to make sure that we have all of our factors dialed in. So we're going to spend the remainder of our time looking at this data set, building progressively more complex models while also visualizing the data to some degree. And what else we're going to see is that as we get more complicated models, we're going to find that there are relationships between completely uncorrelated factors, like away from the problem of multicollinearity, that there are factors that have relationships with our response that we just could not pick up in what I'll call less intense models. We'll go with that. So where are we ultimately trying to go? Here are a suite of models that we're going to look at. So we have a generalized regression, we have a standard least squares, we have torch deep learning, we have XGBoost, we have standard least squares, which is via stepwise, and we have this neural. And so if we just kind of lean back and stare at this, we can kind of see how all of these models perform differently. we can see as we go from, say, standard least squares to GenReg to neural, how we're starting to collapse the spread of data around this one-to-one line. We can even see this in the standard least squares. We're only about 80%, 88 for GenReg, 95 for neural. And we're going to kind of progressively improve these models and kind of show why this is one of the better models and how we kind of optimize this model to do what we ultimately want to do. And let's get right into it. All right, so just to orient you to the data, here is our process. Here are our factors. We have 15 of them. We are trying to predict our yield. I have a series of different types of validations that we'll discuss. And then I've already run many models. And so I've already saved all of these out. And so we're going to use these to look at. But I'm going to walk us through the process of how we get from starting to ultimately ending. So whenever I build a model, where I always like to start is the predictor screening. So the predictor screening just is a simple platform in standard jump that allows you to run a bootstrap forest and gives you a rank order of the most important factors. So here we have pressure, voltage, material thickness, particle count, current, temperature, humidity. And then for me, kind of after this point, it really drops off to what I'm going to call very loosely background noise. So we're going to work off of these particular columns to start. So if we throw these into a standard least squares model, we can see that there are some factors that are really driving this: pressure, voltage, current, material thickness, then to a lesser extent, humidity, particle count, and temperature. We see a pretty decent actual versus predicted. We have a pretty decent R squared. But when we come down to our parameter estimates, there is a major red flag. So by default, under this parameter estimates window, this VIF column is typically not viewable or not visible. To turn that on, you're going to right-click, go to columns, and check that VIF. VIF stands for variance inflation factor, and it's just a value to denote how correlated different factors are. Very loosely, a VIF of 10 roughly corresponds to an R squared of about 0.8. So we can see here that we have 135, 82, a series of ones, 135 and 82. This kind of clues us in to the fact that temperature and humidity have some correlation going on, pretty strong, and material thickness and particle count have the same thing. We can see this in another way, and you'll ignore these colors. I was working on something else and have not yet removed them, but we see what I call this the bow tie effect. So here's temperature, and I'll draw your attention to humidity with the yellow box here. And you'll notice as I move around my temperature, the bow tie, or the knot, if you will, of humidity is changing, but the shape is staying very similar. And the same thing, I'll just turn that off for now so we aren't drawing attention. If I look at material thickness versus particle count, that same thing happens. Why is this happening? Well, it's happening because if I have temperature count high, because it's capturing this collinearity, meaning that there is some linear relationship, I have virtually no values where humidity is low. And the opposite is true. When temperature is low, I have virtually no data points when humidity is high. And this means I cannot disentangle exactly what's going on. So when I start to see this type of behavior, I like to go to the multivariate platform to get a better sense of exactly what's going on and just confirm my suspicions. So here we have the multivariate, and I'm just going to jump straight down here and make this nice and big so we can see it. And sure enough, bright red right here, we can see that temperature and humidity are positively correlated, and material thickness and particle count. If we scroll back up to the top, we can see that particle count and material thickness are 0.99, and humidity and temperature are the same. A value of 1 is a perfect correlation. So we can see that these are very highly correlated. And so we're going to kind of see how these issues play out as we build models. And then at the very end, we're going to bring in principal components to show how we can account for these things. And we'll talk a little bit about what they are and how we can use them. So I'm going to jump right down to the generalized regression model. So now we're moving into JMP Pro. So the value of JMP Pro and generalized regression is we have these tools like adaptive methods and estimation methods, and then other tools like lasso, elastic net, ridge, etc. What these do are various types of penalization techniques that kind of help handle overfitting and help handle multicollinearity.